Number 1. The fungal pandemic factory. Palynologist Vivi Vajda and colleagues at Lund University documented this in KPG boundary sediments across New Zealand and North America. Fungal spore concentrations surged by 200 to 300% above the boundary layer. For somewhere between 1,000 and 10,000 years, Earth was a fungal world, dark, warm, and carpeted in decomposing matter. This was paradise for organisms that feed on death. And here is where the scar forms. Arturo Casadevil at Johns Hopkins Bloomberg School of Public Health has spent decades building a case that mammalian body temperature is not just a metabolic feature, it is an antifungal defense. Most fungal species cannot grow above 35 degrees Celsius. Our 37-degree core temperature acts as a thermal barrier that blocks the vast majority of environmental fungi from colonizing our tissues. Reptiles, which run cooler, suffer from far more fungal infections than mammals do. This is why the amphibian-killing chytrid fungus Batrachochytrium dendrobatidis has driven over 90 species to extinction since the 1970s. Amphibians lack the thermal wall, but the KPG fungal bloom created a selection pressure that pushed certain fungal lineages past that wall. Fungi decomposing massive quantities of biomass in warm, composting conditions evolved to tolerate higher and higher temperatures. Cryptococcus neoformans now grows optimally at 37 degrees. Aspergillus fumigatus survives at 55. Casadevil calls this ready-made virulence. These fungi did not evolve to infect mammals. They evolved to survive heat. Infecting mammals was a side effect, a catastrophic one. The World Health Organization issued its first-ever critical priority fungal pathogen list in 2022, naming Cryptococcus, Aspergillus, Candida, and Mucorales. Collectively, fungal infections kill more than 1.5 million people annually. More than malaria, the scar runs deeper still. Candida auris, identified in Japan in 2009, is a multi-drug-resistant fungal pathogen that thrives at mammalian body temperature and is spreading through hospitals on every continent. Researchers at Duke University, including Robert Batt, have shown that global warming is narrowing the thermal gap between environmental temperatures and human body temperature. As the planet heats, more fungi are being trained, just as they were 66 million years ago, to tolerate the temperatures our bodies use as a shield. The asteroid did not just kill the dinosaurs. It built a factory that has been producing our fungal enemies ever since. Number 2. Mercury still cycling from the Deccan Traps. The Deccan Traps in western India represent one of the largest volcanic events in planetary history. Between 68 and 62 million years ago, fissure eruptions poured approximately 1 million cubic kilometers of basalt across what is now the Indian subcontinent. The most violent phase coincided precisely with the KPG boundary at 66 million years ago. Kyle Meyer and colleagues at the University of Michigan documented in 2019 that these eruptions deposited massive mercury anomalies in sediments across the globe. At Bidart, France, mercury concentrations in the KPG boundary layer reached 600 parts per billion, 10 times the normal background level. The mercury was released as gaseous elemental mercury, a form that lingers in the atmosphere for 6 months to 2 years before settling into soils and ocean sediments. Sierra Peterson, also at the University of Michigan, used mercury isotope ratios to fingerprint Deccan-source mercury in sediments as far from India as Texas and New Jersey. This was a global poisoning event. Once deposited in ocean sediments, mercury does not stay put. Sulfate-reducing bacteria on the seafloor convert inorganic mercury into methyl mercury, the organic form that dissolves in fat, accumulates in tissue, and biomagnifies up food chains by a factor of roughly 1 million from water to apex predators. Deep ocean sediment cores from the Pacific show elevated mercury persisting for millions of years after the boundary. The mercury never left, it entered a cycle. The United Nations Environment Programme's Global Mercury Assessment breaks down modern ocean mercury into 3 categories. Approximately 30% comes from recent industrial emissions, roughly 10% comes from ongoing natural sources like volcanoes and weathering, and approximately 60% is recycled legacy mercury, ancient mercury that has been cycling between sediment, water, and atmosphere for geological ages. The Deccan Traps eruptions are one of the single largest contributors to that legacy pool. Lars Erik Heimberger Boveda at the Mediterranean Institute of Oceanography has documented that deep ocean mercury concentrations have roughly tripled since pre-industrial times. But the baseline they tripled from already included Deccan-era mercury. Carl Lamborg at the University of California, Santa Cruz estimated in Nature that the ocean's mixed layer alone contains approximately 60,000 metric tons of mercury. The deep ocean holds far more. This is why tuna, swordfish, and sharks routinely exceed the World Health Organization's guideline of 0.5 micrograms per gram of methylmercury. It is why Arctic permafrost, which contains an estimated 1.656 million metric tons of mercury, some of it volcanically deposited in deep time, is now thawing and releasing that mercury back into active circulation. Helen Amos at Harvard modeled that even if every human mercury source stopped today, ocean concentrations would take centuries to decline to pre-industrial levels. They would never reach pre-Deccan levels. The Minamata Convention, signed in 2013, regulates what humans emit. It cannot regulate what a volcano deposited 66 million years ago. Number 3. The nocturnal bottleneck scarring human DNA. In 2017, Roy Marr and colleagues at Tel Aviv University and University College London published a landmark study in Nature, Ecology, and Evolution. They analyzed the activity patterns of 2,415 living mammalian species and reconstructed the ancestral states using phylogenetic modeling. The conclusion: ancestral mammals were exclusively nocturnal from approximately 166 million years ago, when they first diversified alongside the dinosaurs, until well after the KPG extinction. The first shift to daytime activity did not occur until approximately 52 million years ago, 14 million years after the asteroid. Margaret Walls first proposed this nocturnal bottleneck hypothesis in 1942, but Mayer's team provided the quantitative proof. For over 100 million years, every mammalian ancestor you have lived in the dark, and the genetic consequences are written across your genome. Start with your eyes. Most reptiles and birds have 4 types of cone photoreceptors, giving them tetrachromatic color vision that extends into the ultraviolet. Mammals have 2. The other 2 were lost during the nocturnal bottleneck, and they never came back. The gene SWS1, which in other vertebrates encodes an ultraviolet-sensitive opsin, shows clear signatures of pseudogenization across mammalian lineages. It is broken, degraded, a relic of a visual system that was abandoned because there was no sunlight to see by. Your retina is dominated by rod photoreceptors at a ratio of roughly 20:1 over cones, an extreme bias toward low-light sensitivity that made perfect sense in the Paleocene darkness and makes you functionally inferior to a pigeon in daylight color discrimination. Then consider your skin. Vitamin D synthesis requires ultraviolet B radiation. Approximately 1 billion people worldwide suffer from vitamin D deficiency, a figure that puzzled researchers until the nocturnal bottleneck provided context. Your ancestors spent so long avoiding sunlight that the metabolic pathways for processing UV exposure were not under strong selection for millions of years. When mammals finally re-emerged into daylight, the MC1R gene, which controls melanin production, came under intense selection as populations rapidly readapted to variable UV environments. But the adaptation was incomplete. Human skin remains remarkably vulnerable to UV damage compared to reptilian skin. Melanoma is a disease of an animal that went back into the sun before it was fully ready. Your circadian system carries the deepest scars. The suprachiasmatic nucleus, the brain's master clock, regulates melatonin production on a cycle tuned for darkness activity patterns. Seasonal affective disorder, which affects approximately 5% of American adults, is a dysfunction of photoperiod sensitivity, a system built for consistent nocturnal life that malfunctions when daylight hours change dramatically across seasons. Your chronic insomnia, your jet lag sensitivity, your difficulty adapting to shift work, these are not design flaws. They are the operating specifications of a system engineered for a world where the sun was something to hide from. Borges and colleagues confirmed in 2018 that phototransduction genes across the entire mammalian phylogeny carry widespread signatures of relaxed selection, damage accumulated during 100 million years in the dark that is still present in your DNA tonight. Number 4. The snake explosion. Catherine Klein and colleagues at the University of Bath published the evidence in PLOS Biology in 2021. Using molecular clock estimates calibrated with the fossil record, they demonstrated that while the common ancestor of modern snakes appeared roughly 73 million years ago, the explosive diversification, the moment snakes went from a modest, low-diversity group to a dominant predatory force, began precisely at the KPG boundary. Before the extinction, the snake fossil record shows primarily Madsoidae, an extinct family with limited ecological range. After the extinction, everything changed. The KPG removed 75% of all species. Small theropod dinosaurs that had occupied ground predator niches vanished. Burrowing reptiles that had competed with snakes for subterranean habitat disappeared. Small lizards that had filled the same insectivore and small vertebrate predator roles were decimated. Klein's data shows a major shift in snake vertebral morphology at the boundary, body plans evolving rapidly as snakes poured into the ecological vacuum. The results are staggering. Modern snake diversity comprises approximately 4,000 species in over 520 genera. The three great advanced superfamilies: Elapoidea, containing cobras, mambas, and sea snakes; Viperidae, containing vipers and pit vipers; and Colubridae, the largest snake family on Earth, all diversified in the Paleogene, well after the extinction. Pythons and boas radiated into large constrictor niches that had been occupied by small predatory dinosaurs. Sea snakes appeared approximately 33 million years ago, invading marine habitats that would have been impossible while marine reptiles still ruled the oceans. Daniel Roboski at the University of Michigan demonstrated that snake speciation rates are among the highest of any vertebrate group. The diversification engine that ignited at the KPG boundary never fully slowed down. Brian Fry and colleagues documented that venom toxin gene families underwent rapid duplication and functional diversification during the Paleogene, as snakes evolved increasingly sophisticated chemical weapons to subdue the warm-blooded mammals that were simultaneously diversifying as prey. The heat-sensing pit organs of pit vipers evolved in the Eocene, roughly 50 million years ago, infrared detectors specifically designed to locate the warm-blooded mammals that had emerged from the nocturnal bottleneck. The predators and the prey were both products of the same extinction. The Australian elapid radiation is perhaps the most dramatic case. When founding elapid lineages arrived from Asia approximately 10 to 15 million years ago, they encountered a continent with no competing venomous snakes. The result was the most venomous snake fauna on Earth: inland taipans, eastern browns, tiger snakes, all descended from post-KPG stock that traced its origins to the day the asteroid cleared the board. Number 5. The toothless bird bottleneck. Daniel Field and colleagues at the University of Bath published the explanation in Current Biology in 2018. When the Chicxulub asteroid struck, it did not just block sunlight, it incinerated forests. The global firestorm and subsequent impact winter-destroyed tree cover on a planetary scale, and this killed every bird that lived in trees. The Cretaceous had been a golden age for avian diversity. Toothed birds were abundant and ecologically dominant. Hesperornithiforms were tooth-diving birds up to 1.8 meters long that hunted fish in Cretaceous seaways. Ichthyornithiforms were tooth-flying seabirds. And the enantiornithes, the opposite birds, were the most diverse bird group of the Mesozoic, with over 80 known species spread across every continent, filling roles from insectivore to fish-eater to possible nectarivore. Jing-Mai O'Connor at the Field Museum has spent years documenting their ecological breadth. They were the dominant land birds of the Cretaceous. Every single one went extinct. The only birds that survived were a narrow lineage of small, toothless, ground-foraging neornithines, modern birds, which had been a minority group in the Cretaceous. They survived because they did not depend on trees. When the forests burned and the canopy collapsed, tree-dwelling birds had nowhere to go. The ground foragers, already adapted to open and disturbed habitats, scraped through. The genetic evidence is haunting. Matthew Harris and colleagues demonstrated that the genes for tooth development, BMP4, FGF8, and the associated signaling pathways are still present in modern bird genomes. They are not deleted, they are silenced. Harris showed that chicken embryos can be experimentally induced to form tooth-like structures by reactivating these dormant pathways. The blueprint for teeth has been sitting in bird DNA for 66 million years, switched off, unused, because the only lineage that made it through the bottleneck happened to be toothless. What grew from that bottleneck is extraordinary. Santiago Clarimont and Joel Cracraft at the American Museum of Natural History dated the explosive radiation of modern bird orders to a narrow window between 66 and 50 million years ago. From one surviving lineage came everything: the 23-centimeter bee hummingbird and the 2.7-meter ostrich. Flightless birds evolved independently at least 6 times as different lineages re-entered ground niches vacated by the extinction. Vocal learning, the foundation of birdsong, evolved entirely after the KPG. Passeriforms, the songbirds, account for over 6,000 species, more than half of all living birds, and they did not begin diversifying until approximately 47 million years ago in Australia. But the scar is in what is missing. No modern bird fills the role of Hesperornis, a large, toothed marine predator. No modern bird has teeth adapted for crushing, shearing, or gripping prey. The entire class lost a fundamental anatomical structure because the extinction filter was so total that it deleted every lineage that possessed it. Bart Ongenbuller at Yale has shown that the beak evolved gradually in theropod dinosaurs over millions of years, but it was the KPG that eliminated the competition and made beaks the only option. In 2020, Field's team described Asteriornis mastrictensis, the wonder chicken, the oldest known modern bird's skull, dating to just before the boundary. It confirmed that the toothless neornithins were present in the Cretaceous. They were just marginal. The extinction made them everything. Number 6. Chicxulub cenote aquifer. The Chicxulub impact crater is approximately 180 kilometers in diameter, centered near the town of Chicxulub, Puerto on the northern coast of the Yucatan Peninsula. When the asteroid struck 66 million years ago at approximately 20 kilometers per second, it did not just vaporize rock, it fractured the limestone bedrock in a ring pattern around the crater's peak ring and rim. Those fractures became conduits for groundwater. Over millions of years, dissolution widened the fractures into caverns, the cavern roofs collapsed, and the cenotes appeared. There are approximately 1,600 cenotes tracing the buried crater rim in a semicircular arc visible from satellite. Mario Ribolito Vieira, at the Centro de Investigación Científica de Yucatán, documented that cenotes along the crater rim are significantly deeper and more numerous than cenotes elsewhere on the peninsula, a direct fingerprint of impact fracture density. Here's the problem. The Yucatan Peninsula has no surface rivers. None. The entire freshwater supply for approximately 4.5 million people depends on the subterranean karst aquifer, a freshwater lens floating atop denser saltwater, with the mixing zone sitting at roughly 20 to 60 meters depth depending on location. And the same porous, fractured limestone that created this aquifer makes it catastrophically vulnerable. Patricia Beddoes at Northwestern University has measured water flow rates through the cenote conduit system at 1 to 10 kilometers per day. There is no natural filtration. Contaminants introduced at the surface reach the aquifer in hours, not decades. Eugene Perry and colleagues measured nitrate concentrations in Yucatan groundwater exceeding World Health Organization drinking water guidelines in agricultural zones. The Yucatan has approximately 3 million pigs, and waste lagoons routinely overflow directly into cenotes and fractured limestone. Mexico's National Water Commission has classified portions of the aquifer as contaminated based on coliform bacteria, nitrate, and pesticide levels. Eduardo Cejudo at Ecology found pharmaceutical compounds, caffeine, and personal care chemicals in cenote water samples across the peninsula. Tourism has compounded the crisis. The Riviera Maya's explosive development has placed thousands of septic systems and hotel waste streams directly above the aquifer with limited treatment infrastructure. Meanwhile, the IODP-ICDP Expedition 364 in 2016 drilled into the Chicxulub Peak Ring and confirmed the extreme fracturing and porosity of the impact-modified rock. The geology cannot be engineered away. It is what it is, the shattered remnant of an asteroid strike. The Sistema Actun, the world's longest known underwater cave system at over 375 kilometers, flows through this same Chicxulub fractured limestone. Contamination entering any point in the network spreads through the entire system. Roberto Iglesias Prieto at the National Autonomous University of Mexico has warned that the combination of contamination, saltwater intrusion from rising sea levels, and reduced recharge from changing precipitation patterns could produce a freshwater crisis for the Yucatan within decades. 4.5 million people depend on water that flows through the wounds of an asteroid. Number 7. The global fire ecology reset. When the Chicxulub asteroid struck, re-entering ejecta heated the atmosphere globally. Douglas Robertson and colleagues modeled the infrared thermal pulse and estimated it delivered approximately 10 kilowatts per square meter to Earth's surface for several minutes, enough to ignite dry vegetation across most of the planet. Soot deposits at KPG boundary sites worldwide contain an estimated 70 to 260 billion metric tons of carbon. Claire Belcher at the University of Exeter analyzed charcoal morphology at boundary sites and confirmed both crown fires and surface fires. The evidence is consistent with burning roughly 70% of all terrestrial biomass in a single event. The forests that burned were Cretaceous forests, conifers, cycads, and ferns that had dominated land ecosystems for tens of millions of years. These were slow-growing, fire-resistant species that had evolved in relatively fire-free environments. They were not built to regenerate after continent-scale incineration, and they did not regenerate. What replaced them was fundamentally different: Fast-growing angiosperms, flowering plants, colonized the scorched landscape. And angiosperms, as a group, are far more flammable than the gymnosperms they replaced. William Bond and John Keeley argued in Trends in Ecology and Evolution in 2005 that this replacement was the single most important shift in terrestrial fire ecology in the last 100 million years. Fire went from a rare, catastrophic event to a regular, recurring feature of ecosystems worldwide. The change was driven entirely by what was growing, not by atmospheric chemistry. Oxygen levels remained roughly the same before and after the KPG. The modern consequences are everywhere. Australian eucalyptus trees actively promote fire through volatile oil production and the shedding of flammable bark strips that carry flames into the canopy. These are post-KPG evolutionary innovations. California's chaparral, the dense, drought-adapted shrubland that fuels the state's most destructive fires, is a Cenozoic fire-adapted biome that did not exist in the Cretaceous. The savannas of Africa, South America, and Australia collectively burn approximately 330 million hectares every year in fire regimes maintained by grass fire feedback loops. Andrew Scott and Ian Glasspool analyzed charcoal abundance through the geological record and documented a permanent shift in fire frequency and intensity from the late Cretaceous into the Paleogene. John Keeley at the United States Geological Survey documented that fire return intervals in modern fire-adapted ecosystems range from 5 to 50 years. In Cretaceous conifer forests, the estimated intervals were hundreds to thousands of years. The entire fire regime of the modern world operates on a fundamentally different cycle than the one that existed before the extinction. The bitter irony is that modern fire suppression policies, decades of putting out fires to protect property, have created dangerous fuel buildups in ecosystems that evolved with frequent fire. We are not fighting natural fires on natural landscapes. We are fighting post-KPG fires on post-KPG terrain, using strategies designed for a world that hasn't existed for 66 million years. Number 8. The Grass Empire. Grasses, the family Poaceae, first appeared approximately 100 million years ago in the Cretaceous. Caroline Stromberg at the University of Washington has spent years analyzing phytoliths, microscopic silica bodies preserved in fossil soils, and her work shows that for their first 34 million years of existence, grasses were marginal players, understory plants, weeds in the cracks. The Cretaceous was a world of closed canopy forests, conifers, ferns, and early angiosperms creating dense shade that kept grasses suppressed. The KPG changed the equation. When the forests burned and the canopy collapsed, sunlight reached the ground for the first time across vast areas. Erosion stripped nutrient-rich topsoil from deforested slopes. Grasses, with their fast growth rates, shallow fibrous root systems, tolerance for disturbed soils, and ability to regrow from the base after damage, were perfectly suited to colonize the wreckage. They did not take over immediately. The major expansion of grass-dominated ecosystems came in the late Eocene to Oligocene, approximately 34 million years ago, when global cooling further disadvantaged tropical forests and favored drought-tolerant, fire-tolerant, frost-tolerant grasses. But the KPG was the necessary first step. Without the deforestation, there would have been no opening. And the grasses did not just fill the opening, they transformed the planet. C. For photosynthesis, the metabolic pathway that makes tropical grasses extraordinarily efficient in hot, dry, high-light conditions, evolved independently in grasses at least 22 times, with the earliest origins approximately 30 million years ago. Today, grasslands cover roughly 40 million square kilometers, 30% of Earth's ice-free land surface. They are the largest terrestrial biome on the planet. The civilizational consequences are overwhelming. The African savanna, the ecosystem that shaped human evolution, that hosts the megafauna spectacle of lions and elephants and migrating herds, is a grass-created biome. The North American Great Plains, which were forested in the Cretaceous, became the grassland that drove bison evolution, shaped Native American cultures, determined European colonization routes, and now produces a significant fraction of the world's grain. The Eurasian steppe was the ecological foundation for the Scythians, the Mongols, and the Turkic civilizations whose cavalry armies reshaped the political map of the Old World. All of this on grass. And here's the most direct connection to your daily life. 8 of the 10 most important human food crops are grasses: wheat, rice, corn, barley, sorghum, millet, sugarcane, oats. Agriculture itself began approximately 10,000 years ago in grassland-adjacent environments: the Fertile Crescent, the Yangtze River Basin, the Mesoamerican highlands, all regions where grass-dominated ecosystems provided the wild ancestors of crop species. Global food security depends on a plant family that owes its dominance to the KPG extinction. Bruce McFadden at the University of Florida documented how horse dentition evolved in lockstep with grassland expansion, from the low-crowned browsing teeth of Eocene Hyracotherium to the high-crowned, cement-covered grazing teeth of Miocene Merychippus, driven by the abrasive silica phytoliths in grass blades. The grazers co-evolved with the grass. The grass co-evolved with fire. Fine grass fuel carries frequent low-intensity burns that kill woody seedlings and maintain grass dominance. And when that grass cover is lost through overgrazing or climate change, the ecosystem does not revert to forest. It collapses. Desertification in the Sahel, Central Asia, and the American Southwest is fundamentally the failure of a biome that was only ever a post-extinction replacement. Number 9. The fern spike and the biodiversity debt. Robert Schutte at the United States Geological Survey described the phenomenon in 1984. In KPG boundary sediments across the western United States, he found that fern spore concentrations jumped from less than 25% of the pollen spore assemblage below the boundary to 70 to 100% immediately above it. The landscape that emerged from the extinction was not diverse. It was not recovered. It was wall-to-wall ferns. Cyathidites, tree ferns, fast-growing, stress-tolerant colonizers that require no mycorrhizal partnerships, had smothered everything. Vivi Vajda at Lund University conducted the most comprehensive global survey and confirmed that the fern spike occurred on every continent. This was not a regional phenomenon. It was planetary. The modern analogs are instructive. Ferns were the first vascular plants to colonize Krakatoa after the 1883 eruption. They are the first to establish on fresh Hawaiian lava flows. They thrive where nothing else can. But they do not build complex ecosystems. The fern spike lasted between 1,000 and 10,000 years depending on the site, a geological blink, before angiosperm diversity slowly, painfully began to recover. But slowly, in geological terms, means millions of years. Full recovery to pre-extinction biodiversity levels took approximately 10 million years. David Tillman and colleagues formalized the concept of extinction debt in 1994. The idea is devastatingly simple. When habitat is destroyed, not all the species that depend on it die immediately. Many persist for years, decades, even centuries, their populations slowly declining, their genetic diversity narrowing, their reproductive success quietly falling below replacement rate. They are committed to extinction but have not yet arrived there. The forest looks green. The species counts look stable. But the debt is accumulating. The KPG fern spike is the deepest proof this phenomenon exists. For thousands of years after the extinction, Earth's land surface was photosynthetically active, green, and growing, and it was biologically devastated. The fern spike is not a sign of recovery. It is a sign of catastrophe wearing a green mask. The modern parallels are multiplying. Terry Hughes at James Cook University documented that the Great Barrier Reef's 2016 and 2017 bleaching events killed approximately 50% of shallow water corals. The reef is recovering, but the recovery is dominated by fast-growing weedy acropora rather than the slow-growing framework-building species that provided structural complexity. It looks like recovery. It is a coral fern spike. Thomas Lovejoy and Carlos Nobre estimated in 2018 that the Amazon rainforest may be approaching a deforestation tipping point, between 20 and 25% total forest loss, beyond which the moisture cycling that sustains the forest collapses and the system flips to degraded savanna. Green, but not forest. Gerardo Ceballos at the National Autonomous University of Mexico estimated in 2015 that the current extinction rate is approximately 100 times the natural background rate. But the extinction debt, the species already committed to extinction by habitat that has already been destroyed, has not yet been fully realized. The number will climb. The fern spike tells us something essential. An ecosystem can look alive and be functionally dead, and the time it takes to actually recover, 10 million years after the KPG, is a number that should terrify anyone who thinks replanting trees solves the problem. Number 10. The Deccan Traps basalt scar across India. The Deccan Traps is one of the largest volcanic provinces on Earth. It covers approximately 500,000 square kilometers of western and central India, roughly 15% of the country's total land area. At peak extent before erosion, it may have covered 1.5 million square kilometers. The total erupted volume is estimated at 1 million to 2.6 million cubic kilometers of basalt, with individual lava flow units stacked to a total thickness exceeding 2 kilometers in the Western Ghats. You can stand on these steppe basalt terraces and count the layers, each one a separate eruption, each one adding another few meters to the geological scar. The eruptions occurred in distinct pulses between 68 and 62 million years ago, with the most intense phase, the Y subgroup, coinciding with the KPG boundary. Vincent Cortillo first proposed in 1986 that the Deccan volcanism was a primary contributor to the mass extinction, and the debate continues. Gerda Keller at Princeton University has spent decades arguing that the most severe extinction pulse correlates with the most intense volcanic phase rather than the Chicxulub impact. Most researchers now view the extinction as a 1-2 punch, asteroid and volcanism together, but the argument is far from settled. What is settled is the scar. The Deccan basalt has weathered into a distinctive soil called rigor, or black cotton soil, a vertisol with extraordinary clay content and an extreme shrink-swell behavior. When wet, it expands. When dry, it cracks deeply, sometimes more than a meter. This soil covers approximately 800,000 square kilometers of central India and is the foundation of the country's cotton belt. Indian agriculture in Maharashtra, Madhya Pradesh, Karnataka, and Gujarat is built on weathered extinction-era lava. The engineering consequences are severe. The shrink-swell cycle causes chronic structural damage to buildings, roads, bridges, and rail lines. India's national highway system across the Deccan Plateau suffers disproportionate maintenance costs from vertisol-driven subgrade failure. Construction on these soils requires specialized foundations, drilled piers, moisture barriers, structural flexibility that adds significant cost and complexity. The Western Ghats mountain range, a UNESCO World Heritage Site and one of the world's 8 hottest hotspots of biodiversity, is composed almost entirely of Deccan basalt. Its steppe escarpment profile, the distinctive terraced cliffs, is the eroded remnant of stacked lava flows. These mountains intercept monsoon moisture from the Arabian Sea, creating the dramatic wet-dry climate gradient that defines precipitation, agriculture, water resources, and settlement patterns for hundreds of millions of people across peninsular India. The cultural scar is equally visible. The Ajanta and Ellora cave complexes, both UNESCO World Heritage Sites, were carved directly into Deccan basalt. The relatively uniform, fine-grained texture of the volcanic rock made it ideal for monumental rock-cut architecture. Laterite, the iron and aluminum-rich residual soil formed by deep tropical weathering of the basalt, has been used as a building material for temple construction across South India for millennia. Even the hydrology is a scar. Major rivers, the Godavari, Krishna, and Bhima, flow across the Deccan Plateau with their courses and watershed characteristics shaped by the underlying basalt. Groundwater in the region is found primarily in fracture zones and weathered saprolite layers, making well yields unpredictable and directly dependent on local fracture density. Millions of rural Indians draw water from an aquifer system whose behavior is controlled by the cooling and fracturing patterns of 66-million-year-old lava. The Koyna Dam, built on Deccan basalt in Maharashtra, triggered one of the most significant cases of reservoir-induced seismicity, a magnitude 6.3 earthquake in 1967 that killed approximately 180 people. The rock it was built on was already fractured, already stressed, already scarred. 66 million years of erosion have transported Deccan-derived sediment into the Arabian Sea, building the Indus fan, the second-largest submarine fan on Earth. The scar is not just on the surface, it extends to the ocean floor. The connections between these 10 scars are not metaphorical, they are systemic. The mercury released by the Deccan eruptions cycles through food chains populated by the snakes and birds and mammals that diversified after the extinction. The fire regime that replaced Cretaceous forests created the conditions for grass dominance. The fungi that thrived in the post-impact darkness now exploit the thermal biology of mammals that survived by going nocturnal. The cenote aquifer was fractured by the same impact that triggered the firestorm. The fern spike pattern repeats in every degraded ecosystem listed above. These scars are not artifacts, they are active processes. The mercury is still cycling. The fire ecology is still burning on post-apocalyptic terrain. The fungal lineages are still evolving to exploit our body temperature. The grasslands are still maintained by feedback loops that started in the Paleogene. Every one of these systems is running right now, 66 million years after the event that created them. The KPG extinction is often presented as a dramatic ending, the day the dinosaurs died. But endings are simple. What followed was not simple. It was the longest, most consequential aftermath in the history of complex life, and it is still unfolding. When Peter Ward and other extinction researchers describe extinction cascades, they mean exactly this: a single catastrophic event producing consequences that ripple through geological time, reshaping ecosystems, genomes, and geochemistry for millions of years after the initial pulse. Consider what recovery actually looks like on the timescales involved. The KPG extinction eliminated 75% of all species. The biodiversity that rebuilt was not a restoration of the Cretaceous. It was something entirely new. Jack Sepkoski's biodiversity curves show that post-extinction intervals do not return to pre-extinction conditions, they produce fundamentally different ecosystems. The modern world is not a repaired version of the Cretaceous. It is a replacement. Chen and Benton documented in 2012 that post-KPG ecological networks operated on different principles than pre-extinction ones. Some niches were never refilled. There is no modern equivalent of toothed marine birds, no modern equivalent of large-bodied flying reptiles, no modern equivalent of non-avian dinosaurs. These are permanent deletions. The recovery timescale is the most important number in this entire video: 10 million years. That is how long it took terrestrial biodiversity to approach pre-extinction levels after the KPG. Marine recovery was somewhat faster, 4 to 6 million years, but still incomprehensibly long by human standards. Douglas Irwin and David Jablonski have both emphasized that recovery is not just slow, it is directionally different. You never get back what you lost. You get something else. Now consider the present. Gerardo Sabalas, Paul Ehrlich, and Anthony Barnosky have documented that the current extinction rate is approximately 100 times the natural background rate. We are causing species loss at a pace comparable to the great mass extinctions. But we are not an asteroid. An asteroid hits once and stops. We are still going. The deforestation continues, the emissions continue, the habitat destruction continues. The KPG was a single catastrophic pulse, followed by 66 million years of recovery. The sixth extinction is an ongoing, intensifying pressure with no endpoint in sight. Elizabeth Kolbert framed the cumulative human impact as comparable to an asteroid in scale. The KPG scars show us what that comparison actually means. If we lose current biodiversity, what replaces it will not be what we had. It will be the ecological equivalent of the fern spike, opportunistic, simplified, stripped of complexity. Modern weedy species, rats, pigeons, cockroaches, jellyfish, are the fern spores of the sixth extinction, ready to colonize whatever we leave behind. The biodiversity debt from habitat already destroyed has committed species to extinction that we have not yet witnessed disappearing. The bill is still coming. The KPG extinction tells us something else, about what survives and why. The survivors were not the strongest or the most impressive. They were small. They were generalists. They could eat anything, live anywhere, tolerate extremes. The toothless ground-foraging birds survived while the magnificent toothed enantiornithines died. The shrew-sized nocturnal mammals survived while the dinosaurs, the most successful large animal lineage in Earth's history, were erased. Crocodilians survived because they were aquatic, cold-blooded, and could fast for months. Turtles survived because they were shielded, flexible, and aquatic. The modern parallels are uncomfortable. Climate change, habitat loss, and pollution select for the same traits the KPG selected for. Small body size, generalist diet, wide geographic range, high reproductive rate, tolerance for degraded environments. These are the traits of rats and cockroaches, not elephants and orangutans. The KPG already ran this experiment. We know the outcome. The modern world is not a stable baseline being disrupted. It is a post-apocalyptic landscape 66 million years in the making, scarred, reshaped, still running on systems ignited by the original catastrophe. The mercury in your tuna, the fire on the California hillside, the mold in the hospital, the snake in the grass, the bread on your table, the water in the cenote, the fern spike forest growing back after the loggers leave, the black soil cracking in the Indian summer. All of it, traces back to a rock 10 kilometers wide that struck shallow water off the coast of what is now Mexico, 66 million years ago. The scars are not healing. They are the world.